Well, in Japanese writing, we use such kind of characters. So these three mean manifold, and these two statistics. The first three are pronounced Sasaki, Sasaki, which is a popular family name of Japanese. Sasaki Shigeo passed away just 30 years ago at the age of 74 or 75. He introduced so-called Sasakian manifold. So in this talk, I like to explain what a Sasakian statistical manifold is. Okay. So this talk is based on this joint work. Yeah, this page is not necessary for the audience of this session. But I just remarked that for a statistical manifold, K denotes the difference between affine connection of torsion-free nabla and the Levi-Civita connection nabla G. Conversely, for a given Riemannian manifold, if you have a 1-2 tensor field K satisfying these conditions, you can reconstruct nabla by this formula so that it's a statistical structure. Okay. So this page is a brief review of Sasakian manifold. Let MG be a Riemannian manifold. Besides, we consider a vector field Z and 1-1 tensor field phi on it. That is, phi, each point phi maps a tangent vector to a tangent vector. Triple G phi Z is called an almost contact metric structure on M if these formulas hold. That is, Z is a unit vector field belonging to the kernel of phi, and phi can be considered as a almost complex structure of the distribution orthogonal to Z and compatible with the metric. Okay. So if M has such a structure, the dimension should be odd. Definition: an almost contact metric structure G phi Z is said to be Sasakian if this formula holds, namely nabla x phi of y equals G of y Z x minus G of y x Z for each x and y. So in the next page, I like to explain it a little bit more. But anyhow, I have defined Sasakian manifold. Okay. Typical example of Sasakian manifold is unit sphere of odd dimension. The following fact will be useful to understand this example. Fact 1. Let M tilde, G tilde, J tilde be a Kähler manifold. For example, the complex Euclidean space. Let M be a real hypersurface, and N its unit normal vector field. G denotes the induced metric on the hypersurface, and we define Z as a minus J tilde N. So the ambient space is Hermitian. This vector Z is tangent to the hypersurface. and we define phi like this. That is the restriction of J tilde to the hypersurface. Then G phi Z is an almost compact metric structure on the hypersurface. And A hat denotes the shape operator of the hypersurface, which is the key tool to study hypersurface in the classical differential geometry, as you know. So fact says hypersurface is Sasakian if and only if the shape operator A hat satisfies this formula. As you know, the shape operator of the unit sphere is identity. So this holds, and it's Sasakian manifold. Okay. The second fact is more important, but we don't have enough time to explain it. But roughly speaking, Sasakian, an almost contact metric manifold is Sasakian if and only if its cone is scalar manifold. Well, this is our statistical version of a scalar manifold. Let M tilde, G tilde, J tilde be a scalar manifold. And let nabla tilde an affine connection of torsion free, and K tilde the difference between nabla tilde and the Levitt-Pita connection G tilde. This triple is called a holomorphic statistical structure on M tilde. If the pair nabla tilde G tilde is a statistical structure, and if K tilde anti-commutes J tilde. Okay. So this definition is a little bit different from the original one due to Croce. The following is the statistical version of Sasakian manifold. So it's point of this talk. Let M, G, phi, Z be a Sasakian manifold. And let nabla an affine connection of torsion free, and K the difference between the nabla and nabla G. The quadruple is called Sasakian statistical structure if the pair nabla G is a statistical structure and K anti-commutes phi. Okay. So once we get this definition, it seems, how can I say, obvious or trivial. So I want to say natural. Before getting this expression, how to define Sasakian statistical structure was a puzzler for me. Okay, so I like to explain this definition works well. Namely, we can extend the previous fact to our statistical setting. So before that, we have to check an example. It's very important. On unit sphere with the standard Sasakian structures before, we define K by this formula. Kxy equals G of x z, G of y z times z. So it's easy to check that K satisfies our conditions. Then it's Sasakian statistical manifold. And besides, it's of constant sectional curvature 1. I like remark that the notion of sectional curvature for statistical manifold was recently given by Opotsuda and by myself. It's a little bit different from usual notion of sectional curvature. Oh. Okay, sorry. So this is the statistical version of fact 1. Let M tilde, nabla tilde, G tilde, J tilde be a holomorphic statistical manifold. And let M be a real hypersurface. As mentioned before, it has an almost contact metric structure G5Z. And we define nabla HA tau by these formulas, so-called Gauss-Weingarten formula. So I should remark that left-hand side of these formulas, we use nabla tilde, not the Leibniz-Bita connection. The theorem says the real hypersurface is a Sasakian statistical manifold if and only if these formulas hold. The first one is similar to the condition in the previous fact 1. So as you know, in Riemannian submanifold theory, so shape operator A and the second fundamental form H have the same information. So these two conditions are reduced to one formula in the fact 1. It's interesting point, I think. Okay, in the last page, I'll give additional remarks. The first, we have obtained the statistical version of fact 2. The second, if you have something about the spheres, you can hope to get something about hyperbolic spaces. Odd-dimensional hyperbolic space is a typical example of Kemmot's manifold. We gave a statistical version of Kemmot's manifold in this paper. Okay. So in the Riemannian geometry, we have model spaces, Euclidean spaces, spheres, and hyperbolic spaces. We study Riemannian manifold comparing with these spaces. How about statistical manifolds? So I like to know which spaces are models in statistical manifold theory. In other words, for example, what is a statistical sphere? It's a problem, I think. And I hope our previous example will be useful to find it in the near future. Thank you.
this talk, it's joint work with Sergei Grigorin from University of Texas, Rio Grande Valley. So we'll discuss holomorphic or paraholomorphic connections for information geometry, and I'll explain those. So let us recall, like in standard classic information geometry, the geometric structure. First, let's take a closer look at this notion of conjugate connection. Essentially, on the manifold, one can prescribe a metric structure and the affine connection structure quite independently. So given an arbitrary Riemannian metric and arbitrary affine connection, we can construct this so-called the conjugate or G-conjugate connection. Well, by this formula, well, one have to be careful. One have to actually check to see nabla star as defined is indeed an affine connection. And that needs to be checked out, and that can be checked out. Namely, the nabla star can be defined with respect to either of the two slots. And secondly, it's involutive. So both needs to be checked, but it can be checked out. So this is a notion of given an arbitrary connection and given an arbitrary G, you have a conjugate transformation of that connection to get a new connection. So that's nabla star. The second notion, when you gave a G and nabla, is that of Kutazi coupling. Arbitrary given G and nabla, they may not be related in some way. But let us define this relation to be a kind of a coupling relationship between nabla and G. And where this nabla ZG is just a covariant derivative and so forth. And these two notions, namely a G conjugate and a Kutazi couple, they are two different notions which are related, but they extend the standard notion of the Levi-Civita connection in the following way. For the Levi-Civita connection, in terms of the conjugacy, it is a self-conjugate connection. The conjugate is itself. In terms of Kutazi coupling, it is a parallel form of a coupling. That is to say, nabla G is equal 0. Because nabla G is equal 0, 0 equals 0 automatically holds. So essentially, these are the two different ways of extending the classic Levi-Civita coupling between a G and nabla. So the link between these two concepts, the G conjugation and Kutazi coupling, is through this well-known identity. That is to say, the lack of coupling is related to the difference of the torsion of nabla and nabla star. Another way of saying is that if nabla and G are Kutazi coupled, then nabla and nabla star, they have the same torsion. So this can be derived. So then this is more or less known to information geometers. Because of this, we can have two equivalent definitions of a classic statistical manifold. One, due to Kruse, is that in a manifold with G and nabla, if nabla is torsion free, and if G nabla is Kutazi coupled, and by that result, nabla star would also be torsion free. So that would be one definition of a statistical manifold, just based on characterization of G and nabla. We can have a second definition of the statistical manifold due to Lauritsen, where you say there is a pair of conjugate connections and that both are torsion free. So they are just equivalent. Now, let us now switch a little bit and investigate the structure of nabla in the context of a tangent bundle isomorphism. Essentially, it's a map between a section of the tangent bundle. Okay, it's endomorphism of the section of tangent bundle. Examples would be almost complex structure and almost paracomplex structure. I use J for almost complex structure, J square minus identity, and almost paracomplex structure, K square equal identity. In the following, it turns out that we can treat J and K in the same formulation. So we just use the L to represent J or K. When you have this L is splits the tangent manifold, complexified tangent manifold, into two parts. One is called the 1-0 part, the holomorphic part, and the other is called the 0-1 part, the anti-holomorphic part. So essentially what happens is that whenever you have this kind of quadratic operator, L, if you look at its eigenvalues, right, it has two eigenvalues, and the two eigenvalues, you look at the eigenspace associated with each of the eigenvalue, and that results in a direct decomposition of the Tm over a complexified field, or over almost complexified field. But technically it's quite tricky, so it just took a while to really understand the splitting part of the story. So with this L, we can define a transformation of nabla. So this is the material I'm going to introduce and we're going to understand here. So given any nabla, we can induce a nabla L using this L. Okay, L is an operator, so it is defined in this way. So essentially, nabla L is defined as L operates on the Y and then take the inverse. So it's called gauge transformation. So when you have defined this nabla L, you very quickly can verify that for any invertible operators on Tm, this gauge transformation forms a group, so that any two operations of L as a multiplication of the operators would just be a group operations as this L transformation. And furthermore, it can be shown that the average of this nabla and nabla L, it is parallel with respect to L. So nabla and nabla L are equal if and only if nabla L is equal to 0. So in other words, this is a case that actually mirrors the Levi-Civita connection with respect to the metric. So in Levi-Civita connection, we have the L, or we have the nabla and nabla star. The average of it is parallel with respect to G. Here, you have the nabla and nabla L. The average of that is parallel with respect to L. So so you can, in this sense, and furthermore, you can show that the L is involutive. This L transformation is involutive. So the second application results in the original one. So now we have a conjugate transformation under L, basically. Okay. And so this is the operator L. And the operator L is important for consider complex statistical manifold, if we can call it that way. So the goal of the talk is to enhance the statistical structure to some more sophisticated, to some like Hermitian and Kähler-like structures. Okay, so this is the goal. So we introduce this L. Now, with this L, we can also define the Kudazi coupling, which this is done in standard textbook. So the Kudazi coupling of nabla L is defined just in a similar way as defining Kudazi coupling with nabla and G. But moreover, we recently came up, we find that it is useful to define this notion called torsion coupling, and I'll explain why. So torsion coupling of L with nabla is that, so the torsion of the nabla L and the torsion of nabla satisfy this particular relationship. So one or the other, they are equivalent. So when torsion is equal to 0, torsion coupling and Kudazi coupling, they are equivalent. They are just the same. Okay. But torsion coupling is a more relaxed way of coupling nabla with L. And we will show the consequence of this concept. So the consequence of the torsion coupling, in a nutshell, is that it makes L to be integrable. So the Nyquist tensor would vanish. So integrable. So it makes L really an integrable structure. And second, it makes nabla to be holomorphic or para-holomorphic, because here I put parenthesis para means when L is K. If without this parenthesis, it just means L equal J. Okay, so every time you see para parenthesis, that means I'm using either L equal K or L equal J, because they are treated the same way. So torsion coupling is a very interesting coupling, a very strong condition, because it causes L to be integrable, and it causes nabla to be a so-called the holomorphic connection. So this leads to the introduction of the Hermitian manifold or para-Hermitian manifold. So Hermitian manifold or para-Hermitian manifold is the case where you both have a metric and you have this L. L can be J or K. So the coupling between J and G is as follows. Equation 1, that's a standard coupling of J with G, and coupling with J with K is as follows. But it turns out that we can write equivalently, we can write in a unified fashion by this equation. So 3 is a unified expression for 1 and 2. It just depends on if you choose J, J squared equal minus identity. If you choose K, K squared equal plus identity, and they come down to the same identical expression in number 3. That's why we can all treat this as an L. So that's the Hermitian manifold. So Hermitian manifold, essentially, you have a complex structure or paracomplex structure, and you also have the metric structure, and these two are coupled. When J is an almost complex structure, that is, it's not integrable, it's called almost Hermitian or almost para-Hermitian. So now what we have is that we can, so what we have shown in the last 2 years is that given an almost para-Hermitian manifold, okay, we investigate the precise conditions under which this would become a Hermitian or even a Kähler manifold when nabla and G are statistically coupled. In other words, when nabla and G are Kutazi coupled. So in other words, if given a statistical manifold and assume there is a L on the manifold, under what condition would we enhance the statistical manifold to a Hermitian manifold or para-Hermitian manifold, and under what condition can further be enhanced to a Kähler or para-Kähler manifold. So what we find is that, well, so these are the sequence of conditions which are exact. So first, Hermitian manifold or para-Hermitian manifold, this is when G and L are compatible just by the standard definition. Now, when this compatibility is satisfied, plus when nabla G are Kutazi coupled, then this manifold will become, it admits a pair of connections, nabla, which is Kutazi coupled to the G, in addition to the almost Hermitian characteristic of it. So this is the almost Hermitian manifold, but then you have, in addition, a pair of affine connections that's coupled with G only. So we call this almost Kutazi Hermitian manifold. Furthermore, if nabla L is torsion coupled, then it will turn this manifold into a para-Hermitian manifold in which the almost complex structure is integrable and the connections are actually holomorphic connection. On the other hand, if nabla L are Kutazi coupled as opposed to torsion coupled, then this almost Hermitian manifold becomes almost Kähler manifold. And finally, if either this or that is satisfied, plus we have a torsion-free condition, then the manifold becomes a Kähler or para-Kähler manifold. So in other words, we go from a statistical structure to a Hermitian and then to a Kähler. We know exact each of the sequence. And finally, we give precise characterization of the condition when the manifold becomes Kähler or para-Kähler. So along this investigation, we also find a very interesting fact. That is to say, if we have, say, a G conjugate, we can define the conjugate transformation of a nabla with respect to G. So that's called G conjugate. We use nabla star. Likewise, we can also use the symplectic form, omega, and define a symplectic conjugate. Well, again, it has to be checked. It has to be proven that it is a connection. And we checked out, this is a connection. It's well defined, and it's involutive. So we can have the omega conjugate of the connection, nabla star, and we have the L gauge transformation, nabla L. Okay. Now, on a given manifold, if we have G, omega, and L, we have this triplet. We have three transformations of nabla. So what are their relationship? It turns out that they satisfy a very simple relationship. Namely, if we add the identity transformation, then the four transformations of nabla, identity, G conjugate, omega conjugate, L conjugate, or L gauge, they form a four-element commutative and involutive group, and this is called a Klein group. Namely, the second conjugation, the two conjugations of nabla is the same. Two omega conjugation would be the same. Two L conjugation, L gauge would be the identity, and any two successive application become the third, and which is irrespective of the order. So this conclusion holds without any requirement on the nabla. So nabla can have torsion, doesn't have to be quasi-coupled with any of these. So it's a very, very general group structure on the space of all connections. Applying this theorem, what we find is that in the case of the Hermitian or almost Hermitian case, in fact, there are four of these connections, nabla, nabla star, nabla L, and nabla star L. All four connections, they are holomorphic. And, well, okay, let us state the theorem more accurately. That the actual theorem states that when we have four connections, so in the almost Hermitian or almost para-Hermitian case, we have four nablas. If any of them are quasi-coupled to G, and if any of them are torsion coupled to L, then all of them are quasi-coupled to G, and all of them are torsion coupled to L. So in other words, on the in the case of the Hermitian manifold, almost Hermitian manifold, if you have one of those quasi-coupled to G and one of those torsion coupled to L, that makes all four of them. So there are four copies of things, or four copies of connections. So unlike the case of the statistical manifold, you have two copies. On the Hermitian manifold, you have four copies. Well, I mean four connections, one and then three other copy. So you have this. And furthermore, the average of nabla and nabla L and the average of nabla star and nabla delta, these are the symplectic connections. These are symplectic connections. So in this case, we call this a quasi-para-Hermitian or CPH manifold. Now, this is for manifold admit torsion, that's we get Hermitian. For manifold which does not carry torsion, in other words, when the torsion is zero, it turns out that basically we have the coupling of nabla with L and nabla with G and nabla with omega, one implying another. So we have a so-called quasi-Kähler or para-Kähler manifold. So the theorem can be stated as follows. Any statistical manifold would become a Kähler manifold, a para-Kähler manifold, if there exists an almost complex or almost para-complex form L such that it's compatible with G, such that L is compatible with G. That is the condition of the requirement for the Hermitian, and that L is quasi-coupled to nabla, So in the case of the Kähler manifold, and we call this quasi-para-Kähler because it's a special kind of Kähler manifold in which there exists compatible connections. So we make the compatible triple into compatible quadruple. So on these manifolds, not only you have G, omega, L, they're coupled, but also there is an omega that's coupled with all of them. So it's compatible quadruple. For the compatible quadruple case, there's always a dual connection in this scalar manifold. So you have a pair of connections which are coupled with G, omega, and L. And they all live very happily together. Okay. And this is what we call the Kudazi scalar or Kudazi parascalar manifold. So this line of investigation leads to very intriguing kind of possibilities about in thinking the nature of statistical manifold. Because as is well known, scalar manifold is a very, very rigid and very special structure in which metric, symplectic, and complex structures, they live together. They're very rigidly locked. And a subclass of that is called the Calabi-Yau manifold, which is used in string theory. So the fact that statistical manifold can be enhanced to a scalar manifold or parascalar manifold under the conditions that we specify suggests there may be some potential links between statistics, physics, and geometry. So we suggest that there may be some possibility of a grand unification using geometry of theories of physics and theory of statistics. And this is a research program that I've been conducting and advocating. To this end, we show recently that information geometry have a very tight link to geometric mechanics. And it's through the discrete formulation of the geometric mechanics. As a matter of fact, information geometry can be seen as a decoupling of the Hamiltonian and Lagrange systems in physics. In physics, you have the Hamiltonian, you have the Lagrange dynamics. Hamiltonian systems captures the conservation principle, and Lagrange system captures the extremization principle. The two are linked together because of the Legendre transform of the Hamiltonian function and the Lagrange function. In information geometry, this is precisely when we can use the divergence function to describe the decoupling of the Lagrange and the Hamiltonian. So according to this viewpoint, information system would be something that essentially has its own dynamics, the Lagrange dynamics and Hamiltonian dynamics, that need not be coupled with each other through Legendre transformation. So in this viewpoint, information system is a generalization of the mechanical system in which the Hamiltonian and Lagrangian are always coupled. So we have a paper that just comes out in entropy, and this is also along the line of my investigation about the so-called reference representation by duality. So with respect to, say, divergence function, the way you capture the divergence between 2 points, when you switch the order of comparison, and if you switch their underlying representation, if for those of you who were in the earlier talk about the rho and tau embedding function, if you switch the P and Q and switch rho and tau, as we described in the earlier paper with Young Knots, then the divergence function will become the same. So there is a kind of a biduality there in defining the information system. In physics case, this biduality reduced to duality because there is no reference effect. The distance between P and Q and P will be the same. So therefore, so you don't see this kind of reference effect. So this would be the general kind of philosophy in carrying out this line of analysis in trying to understand the nature of dual connections in information geometry. Thank you very much.
Just a brief comment, which unfortunately I can't remember the details, but Yao proved it by solving a complex non-fair equation.
Yes, yes.
Yeah. And he wrote a paper showing that if you solve a real non-fair equation, you find, I can't remember exactly what, something to do with Hessian geometry, some kind of Hessian matrix. I've never seen the paper, but that's got a nice little.
Yeah, thank you, yes. That is exactly the case. So there's a tight connection with the Monge-Ampere equation, Monge-Ampere system, which I recently discovered, or rediscovered, that actually it may well be related to deformation of the Hessian manifold. But the details of that is we're trying to work out. Essentially, the Monge-Ampere equations are the, so I can think about that as a way of deforming like a Hessian system and so forth. So, but there is very deep mathematics work down there. So I was trying to picking up along the way and trying to understand the duality in statistic manifold. Okay, thank you very much. Thank you.